Okay, let us continue a little bit more on the heap natural period of practical offshore and ship structures. Like in last lecture, we just ended by estimating the natural period, heap natural period for a semi-submersible, and I was telling you the reason why the structure evolved the way it is. See, we had this formula, no, this T Z 2 pi root over of mass plus added mass. But this keep coming recurringly. Let me write it directly here, rho g AWP, which is my C. So, as we mentioned, if I want, if Tz has to be higher, my AWP has to be lower, assuming that mass and added mass are more or less constant. Really speaking, mass and added mass are basically function of, you can say, underwater volume, and this you cannot control too much in a practical design. So, what happens therefore is that if I want Tz higher, then I need to lower AWP. On the other hand, see, from statical stability point of view, we require large moment of inertia of water plane area. Because you know that metacentric height equal to Ixx by V, when Ixx is of course the water plane area's moment of inertia about the relevant axis. So, how do you do that? Obviously, as I said, to do this two contradictory things, what we have to do is to simply separate out those water plane area boxes, which is exactly what was done in case of semi submersible. We actually separated out the AWP. So, this gives me large Ix and small AWP, and we found out yesterday that we could do that practically period of 20 seconds or so. 20 seconds means what is the wavelength T of 20 seconds? This is actually wavelength of lambda equal to around 1.5 T square, is around 600 400 meter or so, which is fairly outside the regular wave range. Okay, 1.5 GT. Okay, now this was we discussed that. Let us continue this little bit more, stretch it little bit more on other configuration. Let us take spar platform. This is a new concept that came. You know what they do? They simply, it's simply nothing but a floating cylinder. That's it. The spar platform is nothing but a floating cylinder, perhaps moved. How do I get that here? You see here, obviously here the question comes, it's only one cylinder. So, A is of course reasonably small, but here what happened, see, my question of metacentric height, this we address by lowering the CG. Suppose you have a CG lower, then I do not have to have an BM higher, because if CG is here, B is here, see, CG is here, B is here, M will be here, you get the stability. So, again you see these two questions, maintain stability but increase period by reducing water plane area, satisfied here also. So, this is how it evolved. Again the starting point is that you cannot have, for example, a very small a spar buoy like that, it just won't work, it has to be much deeper, and you will find out that typical examples, this may be 20-30 meter diameter, this may be 80-90 meter, nowadays people have gone to even 100 meter. Okay. Now another important thing, shape wise, swath hull, why did it evolve? Now this means small plain area. I will compare immediately with another vessel, that is catamaran hull, in a minute, which is also a twin hull. See here, this is a small water plane area twin hull. It is a twin hull, but it is small water plane area. How does it look like? If you see this section view, it will look something like that. If you see its water plane area, it will look like that. Which means this is the kind of how the vessel looks like. If you take a picture, you will see that it has got two demi hulls supported by very thin struts. Water plane area is very small, and of course top this thing. See, this is to be contrasted with the catamaran hull. This I will do in a second. Same idea. Get the buoyancy from this semi-submersible. The word semi-submersible came because of that. It is semi-submerged. Water plane area is small. So what happened? Same idea. This boat is moving this side. You see, this particular, we achieve the same thing by reducing AWP, increasing IXX. So I have the stability, I have lower period. In fact, why we do that? What is the primary advantage of swath hull? They are known to be extremely comfortable in waves. They simply have very less motion. Why? Because the periods are very high, they do not get excited. In fact, I have read an analogy that riding on a swath hull is like riding a Mercedes car compared to a very small car. The comfort level is so high. The full purpose of swath hull therefore is basically motion control. Now if you look at from other point of view, resistance etc., you will find it is not that good, because its water plane area is, weighted hull is larger. So this is supposed to be excuse me, good for keeping station. So in the special purposes where you want to make sure that you are making some measurements, you have a stable platform, this is used. But take the other twin hull, catamaran hull, typical catamaran hull. Catamaran hull, which is very common now, it is also a twin hull. In this catamaran hull though, you do not have very small water plane area, remember. As a result, catamaran hulls do not have very high natural period. So they are not as comfortable as that at all. Essentially catamaran hulls strength lies in stability. You are getting actually large IXX, so you are getting large metacentric height. But consequently there is no equivalent reduction in AWP, okay, which was happening in swath hull. In swath hull I had a reduction of AWP along with IXX increase, but here I have only IXX increase because most people want to be on the top and all. So this will allow you to have a higher kg, like pleasure craft, various boats and all that. So catamaran hull is a twin hull, but it is not small water plane area twin hull. So it is not that comfortable. I just wanted to make this point because the word twin hull, one may get an impression that all twin hulls are supposed to be comfortable. No, the water plane area must be small. So this is about this kind of like heave motion. Now we worked it out yesterday, periods in a typical ships, in fact a barge and all that, or rather let me put it this way. You take a cross section of a barge type, typically very large beam, very large depth, okay. Then take an ocean going vessel, then probably take a ship with a like this. If you see progressively, you will find out that most of the boats which are for country, riverine vessels, for example the kind of boats that are used, ferries used to cross Ganges, you have much larger breadth, much larger draft, okay. Why? Because primary thing is stability. but then they are operating in river atmosphere where the waves are very less, and these things you will end up finding T to be maybe just 4 to 6 seconds, the natural heap period. This may be slightly more, maybe 8 to 10 seconds. This may be also maybe say 10, 11 second type. So what we find, obviously, the deeper it is, the draft is higher compared to breadth. Basically, B by T is lower. This gives rise to T higher. T means here draft. You know, this is here draft. Let me put it this and this is the reason why you will find out that riding a small boat is usually more uncomfortable, always more uncomfortable. Remember another thing of interesting, suppose heave motion is ZA, well, cos, of course this is a force oscillation, but let me, I think I will not put it this way. See, if the oscillation frequency is higher, okay, then period acceleration is proportional to omega square ZA. So you have much larger acceleration, you are subjected to much larger acceleration, and obviously it is not good. This makes sense, because if you take 4 seconds to make one cycle, then you know that the speed at which you are going rate is much higher. So if period is low, acceleration low, frequency is high, acceleration becomes, since proportional to square of frequency, very high, and if it's very high you do not like it because it's very uncomfortable. One of the reasons why small boats are always uncomfortable is that, you know, compared to a larger boat, in terms of comfort usually. Okay. So these are all kind of practical values, we will get back to this afterwards, but typically our aim would be to be, you know, like around this range. The other point here, having said that, is what I said yesterday, once again I will repeat it, that these all are lying between my practical wave range, what is known as everyday wave frequency range, which is between say approximately say 5 to say 15 seconds or so. I mean, if you go to open ocean, in fact one can narrow it down to more like 8 to 12 seconds. Typical open ocean waves are approximately 100 to 300 meter long. Typical ship lengths are also of that length. Typical periods, heap period, correspond to that wavelength. So there is really no escape for ships, and it is somewhat very close by. But for offshore structure, by design you are doing it away. And the reason I mentioned yesterday that ships, I have a provision to get away from resonance by lowering speed and by changing heading, which I do not have in offshore structure. Secondly, I do not have the limiting operation as in offshore structure for heave. In there I have to stop operation if my heave is excessive, downtime is very high, etc. So in fact the full research is going on. Recently also in our conference there was a paper which was called ultra low motion semi submersible. Okay. You do not talk of ultra low motion ships normally because it is not that critical, but here it is important not for comfort, for operation point of view. Okay. So this is about, we will get back to this combined thing again. Now what I will do, I am going to switch to the next motion, pitch. See, heave, pitch, roll, especially heave and pitch, they are all similar, just that the equation form will look different, but the solution remains similar. Now if I now go back to, switch back to pitch motion, of course, you know, this is my x, my y, this is z, and pitch is going to be this motion, say theta. Remember, it is always good to use a consistent axis system. So if I have y to be port side here, you can see that is, then bow up is going to be my positive pitch according to this diagram, right? No, sorry, let me see how it is. So no, sorry, I think it is I'm just the opposite, right? Positive will be this way, positive is bow down, sorry, the theta positive, I must correct it here. If y is here, my positive theta is bow down, but it does not matter for my what I am going to tell purpose. You see, this is a right hand system. So, bow down is going to be positive pitch. Now, what is the equation of motion for that? Single degree equation of motion. Just like heap, I am going to have here I moment of inertia about of rigid body about which axis? Y, because we are, remember, going through the center of gravity, because this is my origin that we have defined. We have defined the motions with respect to coordinate at CG. So, IYY, let me write it down, plus there is going to be, let me write it this way, this is added it does not matter how we are calling it. We can call it, this is cos, maybe plus here some beta theta. See, what I wrote here is exactly same form of equation of motion. This is just like m x dot dot for rotational motion. You have, what do we have? We have rigid body moment of inertia about the relevant axis y y. So, this is, and please understand, rigid body moment of inertia. It is not to be confused with Ixx or Iyy that you use in hydrostatics for water plane area. Okay. It is mass moment of inertia. Lots of students normally make this mistake, maybe for symbol or so, because in hydrostatics we use Ixx, Iyy as moment of inertia of water plane area. This is rigid body mass moment of inertia. Not to be confused whatsoever. This exactly the same thing, added mass, basically these two, just like what we had earlier, added moment of inertia and damping moment, where we are calling moment because it is moments now, not forces. Basically this part is that added moment force. So, this is, you can say, added pitch, added mass in pitch, and this is damping for pitch, pitch damping. So, this is like pitch, well, we can call it this way, pitch added moment of inertia. Instead of mass, we can call it moment of inertia, and this is pitch damping, and this of course is pitch restoring moment, hydrostatic restoring moment. And this is of course the pitch exciting moment, exactly the same, the form is same, everything is same, the solution also will be same. Of course, this m theta is the amplitude and this is of course the time. So, the full thing is the moment of inertia. So, you see, if you look at that, in fact, if I did not call it, the solution is just same as what we have done before, exactly same, there is no only the terms change. This is actually m plus a z, z dot dot, b z, z dot, c z, z, etc. So, solution is exactly same, it will look similarly like this, like this, like this, etc. There is going to be natural period, like this omega, this is going to be this omega e equal to omega theta. Omega theta is natural period. So, natural period, natural pitch, well, frequency rather, pitch frequency is going to be square root of c theta by I plus in my here delta I y y, etc., etc. So, the the natural period, say t theta is going to be 2 pi square root of I y y plus delta I y y plus by c theta. Okay, exactly same as before. So, there is really not much to talk about the nature. What we need to talk is what are these terms, how much are these terms, therefore, what is the estimate of t theta and how do I lower it. As far as the formula is concerned, you may even think that as the numbers go, this is like mass, this is like the added mass in heave, this is like restoring force. Just pitch that it is the word, you can just cut the word heave and use the word pitch, that is all. So, therefore, as far as the solution is concerned of the equation of motion, there is nothing extra. That is why I spend so much time on the heave part, because single degree of freedom equation solution nature will be looking exactly same. Oh, okay. Now, yeah, okay, all right, okay. Now, good question. Let us discuss the physics of where did this added moment of inertia come in this case. Very relevant question. See here. Okay. Now, I am rotating it. What happened to this section? It tries to come down. What happened to this section? It tries to go up. So, what happened to this fluid particle here? Gets pushed down. What happened to this fluid particle here? Some disturbance is here. So, what happened? There is a general mass of fluid particle again getting disturbed. Now, you see, when I rotate it about this axis, I have I y y theta dot dot as moment of inertia. For any rigid body, if I take a rigid body, moment of inertia. Now, here same thing, along with that some mass of water is also have to be rotated. You see here, when I am pushing it down, this water gets pushed down. So, it is like again so much of water. If I were to show a picture with a rate, as if so much of water is attached to it and getting rotated. This is the origin, because whenever I am accelerating, there is some amount of water that is also getting accelerated. In this case, this comes down, this goes up, therefore, as if the mass of the section becomes heavier with this amount of mass. So, if I take moment of inertia, it is this mass plus this mass. This is the origin, same thing. See, any modes of motion, whether rotation or whether linear, we are necessarily pushing water and accelerating surrounding water. So, the surrounding water acts as if it is part of this mass. The difference being here is that I have to take moment of inertia of that mass for rotational modes of motion. As I said, if I were to take a small piece of mass here, see this red piece of mass, this fluid particle, this particle is also getting accelerated down. So, therefore, what is my moment of inertia? Mass of this section distance square plus mass of this particle distance square. So, if I integrate that, I end up getting a contribution from the mass of the fluid particles. This is what is added moment of inertia. Okay. So, added moment of inertia will also come in any accelerating motion. Remember, this is an acceleration motion because I am just accelerating it. So, moment I do that, there is an acceleration. If I was steadily keeping like a trim, there is no added moment of inertia. Like when I shifted a weight, it trimmed. There is no concept of added moment of inertia, or rather this force does not apply. All right. So, we will get back to this c theta part. Okay. This is what, from here only I can tell. Tell me, I will only ask you this question. If I were to trim the ship by an angle theta, what is my restoring moment? What is the moment that is trying to bring it back? What is the so called pitch what I should say in case of trim, the trimming moment. See, it is given by weight into g z in longitudinal direction, or I can say g m l into theta. Actually, because in pitch axis theta is always small, so we always write that way. in reality, and you have seen the trim cannot be more than 2-3 degrees, because if it was so, the bow would have come up. So trim is always very small. So it is W into weight into GML into theta. This is my trimming moment M, right. That is what we have done always. If you shift a weight here, what happened? W into D equal to W GML theta, and this GML you write as TPC, etc., etc. Not TPC, sorry, MCT, moment to change trim. So, but our case it is like that. So what is W? W, it is, I always prefer to use this in a SI unit. SI unit means it's force into distance. Force meaning mass into acceleration. Okay, so therefore what I do, it is I write now mass. Sometime people write trimming moment as confusion we always had ton meter. Actually it is ton force meter. So it is always good to use consistent SI unit. So I prefer to write this as rho GV, because there is no ambiguity. If you write this as rho G into M, sometime people don't take G, etc. So if you use that, this becomes fully consistent. Newton. Rho, no confusion, it is mass by length cube. G, no confusion, this no confusion. So this into GML, okay, into theta. This is my C theta. What it means is that if I were to, just like in heave, if I were to trim it or pitch it by theta degree, there is a moment trying to restore back of this amount. Okay. If I, once again, if I trim a hull like this, well, if I trimmed a hull like this, the moment comes in trying to restore it back, and that is given by this into theta. Larger is linear with respect to theta, and therefore this is my, as you know very well, for estimate purpose for ship, sometime I can use GML equal to BML, approximately, but that is for ship, we do not have to do it, but this is my basic formula. Okay. So this GML is known. Now we will get back to again this part. Let us again have an estimate Ix, Iyy, etc. First of all, let us look at Iyy. You see here, this is my ship, this is my axis. What I am doing, I want to find Iyy. How I can write Iyy? It is actually mass into, you can say, Kyy square, when Kyy is radius of gyration about the y axis. Okay, this is the relevant radius of gyration. Now tell me, just from estimate, these masses are more or less distributed going lower, etc. See, suppose you take a cylinder, uniformly distributed mass. You can find out Kyy, you know that it will be somewhere around here. Well, I do not recall, but it will be something like something by root 12, etc. What I mean is that if these are difficult to estimate. How do I estimate? I actually have to go to weight curve. I actually have to go to the weight distribution curve, then take sectional weight, then take square of that, integrate them, etc., etc. But quite often getting weight curve of a ship is one of the most, not difficult but uncertain things, because a lot of waves come here and there all the time. So for our purpose, we can make a reasonably good estimate. What will be a good estimate? A good estimate will be that if it is around L by 4, moment of inertia, Kyy, around that, not necessarily, maybe around 25% to 30%. You see, what happens is, let's take a logical guess. If the mass was uniformly distributed like a cylinder, moment of inertia is going to lie between somewhere here, because you see the masses which are further contributes more. So if you see, in fact, mx square and integrate, you will find here. Okay. So if there is uniform distribution of mass, that means if mass was uniformly distributed, it is something like 35% or so, I think 33-35% of length. But in the ship case, what happened, you understand that masses are more in the center region, sections are bigger. As you go to edge, typically you have smaller section, smaller mass. On the other hand, they contribute more. So, it is very logical. Number one, it can never be at 0.5 because 0.5 would mean as if all the mass is here, it cannot be at the center. So, it appears from any practical point, and it has been borne out from large number of measurements, that it is around 25%. Well, 25, 25, 27, 28, 30, something like that. So, you can more or less say KYY is approximately, you know, like 25 to say 30% of L. This is a guess though, one can always say why 25, why not 22, yes, but for you will find out that the difference will not be so much in the prediction, number one. Number two, really you cannot hit the exact number, whichever way you do, it is an estimate. So, this is okay. And now comes to, so what I am trying to get at is that we want to make an estimate for real structure, this value. Again it is necessary at what period I have an excessive pitch. So, I need to estimate this and this for a real shape. Okay. Now, let us look at IYY part, the delta IYY part, that added moment of inertia. Now, once again here we will look at this way. So, if I have this shape here, take this section. Now, if this section is this section. Now, when this section is undergoing, like the body is undergoing rotation, this is trying to come down. The question is, what is the kind of mass attached to it approximately if I take the same acceleration? Remember that is a sectional added mass in heave. That is the mass you would expect to be attached to this going down. Sectional added mass in this direction is what is the added mass of this contribution. So, if I take that and square the distance and add it up, then I end up getting so called the added moment of inertia approximately once again. Now, again you find out that we have discussed last class, a good estimate of that is that it is mass of the water of this surrounding semicircle. So, what it means is that this becomes again approximately the added moment of inertia of water mass having this, you know, like semicircular body, just like the mass would be, heave added mass would be mass of that, pitch moment of inertia would be moment of inertia of that. In other words, something like this, if I were to draw in a different color, as if this was the ship here, and as if there is a another geometry, you know, like a kind of a geometry which is semicircular in look, but top is actually same breadth. Mass of that becomes approximately the added mass in heave, moment of inertia of that becomes approximately the moment of inertia for pitch. So, obviously, if you look at this again you will end up finding that your delta IYY is approximate, which also I can write k dash yy square into mass. I can write in this fashion if I want. This turns out to be almost equal to 0.25. In other words, this is very comparable to my IYY, just like the other case we have found. So, therefore, if I were to write this, you know, IYY plus delta IY, delta, what did I write? Delta IYY, is it? Let me see. So, I can write this as IYY into 1 plus some factor, say some CYY, say this, I can always call CYY to be, you know, like added moment of inertia divided by rigid body moment of inertia. So, this turns out to be again around 1.5 like that, the factor, just like what we have done before. So, this added moment of inertia plus moment of inertia, which can be called virtual moment of inertia, may be around 2.5 times rigid body moment of inertia approximately. So, you see the CYY of course by definition is the coefficient, that is delta IYY by IYY. So, this is around 1 to 2, maybe lower, maybe higher, in that order, exactly same as what happened for the heave added mass. So, we will take this as benchmark for our estimates, for, you know, like doing certain estimates here. Okay. Now, now let us go back to the estimates. All right. So, let me write this again, then T theta. Then what was that? 2 pi I am spending long time in the natural period estimates, because remember, when you do a design, you don't have a control on the environment, but we have a control on the geometry and the mass distribution which decide natural period. So, I need to have an idea what it should be, where it is, how much it is, and can I play around with this, what I should change to change it, etc., etc. That is why we are playing with that much, because our aim is always to ensure that they do not coincide. If it coincides, how I can get away, and all this stuff. So, this was if I were to take Iyy outside, let us see, it is 1 plus Cy, that is what I wrote here, and let us see, this is rho g v into GML. Now, I will do one thing, I will write this Iyy as mass is rho into V, remember, into kyy square, right. See, Iyy is what? Mass into kyy square. Mass is nothing but rho into volume into k square yy. Agreed? So, this into kyy square 1 plus Cy by rho g v GML. So, I have this gone, this gone, this gone, this gone. So, this turns out to be 2 pi kyy square comes out this thing here 1 plus Cy by G into GML, something like that. Okay. So, this is okay, no? This is kyy outside. Now, you see, let me put it this again, this 2 pi kyy, I told you I can write kyy a proportional to, let me write it now as a factor, let me call it at FL, when f of course I said was 0.25 or so. If okay, let us write in terms of like that. So, this say I call it f into L, well okay, let us call it this is 1 plus Cy, and G is here. Now, GML, remember, in for ships typically GM is order of length, right, it is very large number 150 etc. We can also call this again, say, well, if I call it F1L, I can call this F2L, say I call it, where I tell you why I wrote that. F2 is typically what value, 1, 1.5 like that, around 1, F1 is around 0.25. Okay. Now, let us put these numbers here, this one will get back to this for a typical ship. This is only valid for a ship, remember, because I use this L part. For a semi submersible it will be slightly different, because semi submersible GML really is not order of length, it is much smaller, because for semi submersible GML GMT are of same order, both of which are higher than GMT typical ships, but much lower than GML. We will come to that. So, if I look, in other words, for semi submersible you really have no preference on x and y axis, but here let us take a ship length of 100 200 meter, I mean typical. So, if I have 200 meter here, let us go back to this next one, say L is about 200 meter, say Cy I am taking 1, which is quite reasonable. Now, this becomes C, I will take F1 is 0.25. So, I have got 0.25 into 200, okay, root of R of 2 by G is about 10, F2L is again 200. So, this will turn out to be, let us see how much it comes, this is 100, is this, let me try to find out if this is okay. This is coming to be 100 here, 1 by 2 pi into, this is 50, right, into square root of 1 by something like that. Let us see how much this is. This is this into 50 into 2 into about 9 point around 10. What I got is around 10 seconds. Okay. So, again you see interestingly, once again for a large ship, my T theta is 10 seconds. Okay. So, once again we are for pitch middle of the wave spectrum for a large ship. Now, I will leave it to you to work out for smaller boats, and you will find out it will be also something like 7, 8, 9 seconds. Okay. So, again see we are in a problem of that. Now, let us see what we can do. Typically, if I again look back to that, see IYY, really speaking you cannot change much. Actually, this formula, if I go back to that, F1L you cannot really change much, it is like that always. F2 also, see it depends on F1, F2 and CY. CY also is a geometry, typically it will remain around 1 to 2. Okay. In fact, if there is 2 there, so the difference is that if it is 1, it will be root 2. So, the factor is 1.4. If it was 2, root 3 means 1.7. So, basically it will differ by something like 13, 15 means 20%. 10 would have become maybe 12, but it will still be within that range. So, my point is, of course, we are not hitting the exact number range. 8 to 12 seconds, if I were to stretch both sides for a large ship, he also was like that, 8 to 12 seconds. So, we are in trouble for a ship. Not in trouble, but we cannot avoid it. It is just an unfortunate consequence of that. So, we have this unfortunate consequence for a ship. Let us look at semi-submersible now, or some spar or something, offshore structure, because remember we are doing this also as a part of ocean engineering. So, you also have to have an idea of floating offshore structures, and in fact, for floating offshore structure, these things are much more important from design point itself, these motions. Let us take an example, then only we can probably do this. Okay. Often I will tell you a twin, something like a twin pontoon, a typical semi-submersible, let us take, it looks like that, like the side view, plan view, there are 2 there, this say this is about 100 meter, say this is about 6, so the width is about 15. I mean, I am just telling these are all kind of realistic numbers, this may be about 8 meter. These are all kind of like realistic kind of number. Typical values are like that, 8 to 10 meter, you can take 10 also if you want, 90 to 100 meter, this is about 6 to 8 meter, width is 15 meter. You see the displacement, you can work it out equal to how much, 2 into 100 into 6 into 15, that is the pontoon, plus okay, let us also take this may be, the draft may be about 20 meter, let us say 20, that means this is about 14, right. It's all very rough number. I am just trying to, but they are realistic number. When we are doing an engineering course, we need to, I have always retained that, we need to always make guesses which are of right order. So, this is this and this is how much, this is 4 times, just tell me quickly, this 4 into pi into, well actually 8 square by 4, right, this 4 gets into of course the height 14. So, this will come around, let me just try to do this, 2 into 100 into 6 into 15, this is 18,000 plus this becomes 8 square into pi into 14 is about 2800, right, say around 2800. You can of course see immediately that contribution of this is so much smaller than this. So, essentially the buoyancy comes from this and the waterline support comes. This is why these things are known as column stabilized semi-submersible. Columns are stabilizing it. See, these words for these are column stabilized semi-submersible. Semi-submersible because buoyancy is below. Columns are stabilizing it. Anyhow, this comes to around 20, say around 21,000. Let me put it this way. Now you see, okay, let's put this some number. How much do you think for this one the a good value for KYY is going to be? Now you see this is a more or less box here. This is what contributes. So 25% of this is about 25 meter. But because of the cylinder, maybe I'll make it a little more. Let's say make it 30 meter because the cylinder will push something out. So let's call KYY around 30 meter. Okay. This is quite a good guess because remember these columns will push out slightly. So K dash YY, I'll make it 1 for that purpose. And another thing is I need GML, right? Now remember here GML, this kind of bodies, the GML is going to be much lower than 100 meter, much lower. In fact, if you want to make a guess, we can also make a guess, buoyancy and all that. Buoyancy will turn out to be something somewhere here, KB. And if you do BM, it will come something like, because I is much smaller. So this will turn out to be about maybe around 5 to 10 meter, something like that. 8 to 10, let's put it at 8 meter or so. It will not be 100 meter because I is much smaller, much smaller. But see 8 is quite okay. Remember for a ship, GMT, what is the order of GMT? Only 1 meter, 2 meter. Actually the rule says only 15 centimeter is good enough, right? But we have 1 or 2 meter. GML is 100 meter, but this case GML and GMT are of same order. Both are something like 8 meter or so, 8, 10, 5 like that. And remember this is safe enough. So there is no issue with safety at all. So let's call it at around 8 meter. So now we will go back to this formula, try to see what is this thing. Again we will find out that similar part would happen, say T theta equal to 2 pi, we will write it this way here, okay, 1 plus Cy by G into GML into here, of course I had KYY. So this KYY I say 30 meter is 2 pi root over of say 2 by 10 into say, let's put it 10 only, you know, GML, instead of, let's make it 10, easier to calculate. How much it comes to? Let us work it out. This 2 divided by 100, right? Square root of that into 2 into pi into say 30, 26. Absolutely good. See here what we find, T pitch again very high. See look, T he was around 20 or more than 20 or so in that order. T pitch is also something like much more than 25 or so or 20 or so. Means both of these by design we are far from the everyday wave. Absolutely good. Therefore, again if I look at why it is so, you can easily make out from here. See in the ship GML is much higher. If this is higher, this is lower. But yes, but whereas semi-submersible this is relatively much lower, something like 1/10 time here. So 1/10 means, you know, factor of 1 by root 3, 1 by 10 square root means 1/3. So it's almost 3 times more. It's 8 seconds, means 24 seconds. So this is very good news, because we don't want any natural period of any motion close by to everyday wave. So this is again, you see the very interesting thing happened. Okay. And that is again a part of your design. And why did it get it? Again the same thing. Why was GML small? Because my BML is small. Why BML small? Because my I was small. Well, not too small, but small enough, because A is small. Remember my semi-submersible water plate area is this. Whether you take about this axis, that axis, more or less similar. Both are similar. Ship, take this axis, much smaller, take this axis, much larger. So here I have got equal bias both sides, GML is much lower, and I end up getting this very nice thing that it is like this. And of course you have to design it for that. So suppose somebody wants to design and you kind of change these values, you make it much bigger, much smaller, etc. You will end up getting a much lower natural period. If you increase this, AWP goes up, decrease this, mass goes down. You will find out, suppose you get more volume from the cylinders, which would imply less volume from here, which would imply you are getting AWP more, I more, which would imply GML much higher, lower T. So there is a balance. That is very important. Now, before at the beginning of the class, I talk about spar buoy also. This is a new concept, spar. You know, everybody wants to simplify it. What is a spar? Just simply a cylinder, vertical circular cylinder. That's a spar buoy. A new, in fact, this concept, or not a spar buoy, it's a spar platform. When it was proposed, a company was formed called Spar International. You know, when originally proposed, and offshore structures are always evolving. See, the interesting part of offshore design is that ships are typical ship-like structure, long, narrow. All you play around with the section shape, aft form, etc. But generic change in form, that is whether it look like box type or this type or some semi-symmetrical type, all these are possible only in offshore structures. Much wider variety of design. But when you do that, you have to remember this thing. This forms a very critical part. Natural period has to be over 20, 18, 20 at least. So here what we are doing, you can see here, this is not a problem, because in this case again GML, which is of course, you know, like in a sense proportional to, well, you can say I of moment water area by, actually this thing GML and GMT are same because it is a circular cylinder. Both GML, GMT are of the same order. What people do, of course, is they play around with the center of gravity. That is why it is so much lower. So G can be somewhere here. So I can always see my B is here. I can always tune it and put G in such a way so that I get the enough GML, not very high. We of course don't get very high, but not very low either. See, remember, as far as this is concerned, there is no difference between GML and GMT, they are same. So in a ship GMT is much lower, GML is much higher, but it is both are same. How do I control it? Obviously I want to have minimum value of GM, let me call it GM here in one word, because GML, GMT same. Okay. So how do I control it? I control it simply by playing with the G. Normally, of course, with all design comes. Again, if you put the numbers here, you will find out any book will give you this kind of typical evaluation of spar, the kind of, this may be 30, 40 meter diameter, this may be 80 meter, 90 meter depth. You will end up getting that a part of the design of spar or whatever is to make sure that you end up getting period about again 18-20 second or more. So 18-20 second or more is basically necessary from design. In other words, if I were to do a spar, thinking that, oh, I will just make a spar like that, you will see it will not work. Now this brings a question to our mind about FPSO, which is a typical tanker hull type, you know, FPSO if you see. I just want to, before end of this lecture, talk about this also, because FPSO are nothing but a tanker hull. But you will find out that typical FPSO tend to have a much deeper draft. The section shape tend to be much more like that. Why you do that deeper? Because you know, if you do deeper draft, you end up getting, we have seen that in Heap natural period, and this pitch will be same thing, is inversely proportional to T. Make a deeper depth, your natural period goes up. So this is why FPSO's typical natural periods are not so much as 20 and all, it may be around 15 or so, but at least you try to make it push to 15, 16, not keep down to lower as 8, 10. And how do you achieve it? Basically making a deeper draft. Remember, this is in one station, so my requirement regarding freeboard etc. are less. When you convert a tanker, you have less choice, but when you design from beforehand, you have more choice, and you will always find, if you take an first design FPSO with a tanker, you compare it, you will find that the FPSOs are deeper. So you know, again why it is so? Because there is a tendency, of course, one thing is you have more volume, but volume I can always get by making a broader beam, but you don't do that. You do that deeper because you necessarily want to push the natural period up. This is the logic behind the evolving the structure. So I'll end this lecture, this hour, by saying that this natural period, heave and pitch, we have seen, very important. When you are doing specially offshore kind of structure, you have to keep in mind in your forefront when you are evolving a design. Without doing that and seeing in a ship, we do post process. After the design is done, we try to check as a verification, or you can say as a post, you know, like study how much what was the period. Here you cannot do it. So with that I'll stop this hour. We will go to the next in a minute.